Welcome back, everyone. India is moving ahead with advanced trials in sixth-generation communication systems as part of its plan to lead in future wireless technologies. While 5G is still being rolled out across much of the country, top research institutes and telecom firms are already collaborating on prototypes for 6G. These systems promise to deliver speeds over 100 times faster than 5G, along with ultra-low latency and real-time response. 6G will enable applications such as holographic communication, precision robotics, and immersive extended reality. India's trials include new spectrum experiments, terahertz signal transmission, and development of indigenous hardware. By entering early-stage testing, India is positioning itself to shape future global communication standards rather than waiting for them to be defined elsewhere. India's 6G systems will operate on extremely high-frequency bands known as terahertz waves. These frequencies can carry far more data than the microwave spectrum used by 5G and earlier networks. However, terahertz signals do not travel very far and are easily blocked by buildings or trees. To overcome this limitation, Indian researchers are developing small cell-based stations that can be densely placed throughout urban and semi-urban environments. These micro-base stations will create overlapping coverage zones that allow seamless handoffs and uninterrupted connectivity. The infrastructure will require a combination of fiber optic links, edge computing nodes, and wireless relay units to ensure consistent performance across the network. One of the defining features of 6G will be its use of artificial intelligence to manage the entire communication process. In India, engineers are designing systems where machine learning algorithms optimize data routing, network slicing, and power allocation in real time. Unlike static rule-based configurations used in earlier generations, 6G networks will adapt automatically to user behavior, network conditions, and traffic volume. This dynamic adjustment will help maximize bandwidth and reduce congestion. Indian software development teams are building frameworks that allow telecom equipment to learn from past data and improve network reliability without human intervention. Signal transmission in 6G will be based on advanced modulation schemes that allow more bits of information to be packed into each wave cycle. Indian laboratories are experimenting with higher-order quadrature amplitude modulation, time-domain multiplexing, and beamforming strategies. These techniques increase throughput by optimizing how data is embedded into electromagnetic waves. Beamforming in particular allows antennas to direct signals precisely toward the receiver rather than broadcasting in all directions. By concentrating energy in this way, Indian 6G systems can reduce interference, improve range, and support multiple simultaneous connections without sacrificing performance. India's 6G architecture will depend heavily on edge computing to reduce latency and improve responsiveness. Instead of sending all data to central servers, the network will process information close to the user at edge nodes, located within the base stations or nearby devices. This is especially important for applications that require real-time feedback, such as autonomous drones or remote surgery. Engineers in India are working on low-power edge processors that can run complex analytics on the spot. These processors will be connected through ultra-fast links to the core cloud infrastructure, allowing for both local responsiveness and large-scale coordination. Smart surfaces and intelligent materials will play a role in extending 6G coverage in India's dense cities and rugged rural zones. Researchers are testing reconfigurable intelligent surfaces that can reflect and steer terahertz signals toward users, even when there is no direct line of sight. These surfaces are embedded with electronic components that can adjust their reflection patterns in real time. When installed on walls, poles, or ceilings, they can help overcome signal loss and ensure consistent quality. These passive relay systems require no power and can be manufactured at scale for affordable deployment across a wide variety of environments. Device connectivity will also see major improvements under India's 6G network. Future smartphones, wearable devices, and industrial sensors will use multiband communication systems that can switch between terahertz, millimeter wave, and traditional spectrum depending on the environment. This flexibility allows uninterrupted performance in both crowded urban areas and remote regions. Indian electronics manufacturers are designing new chipsets that integrate multiple antennas and signal processors in a compact package. These chips will also support encryption, signal authentication, and adaptive power management to improve security and battery life. Device-level intelligence will be critical for smooth interaction with the broader 6G infrastructure. Security protocols in India's 6G systems will be integrated right at the core of the network, rather than being added later as an external feature. Each device will have a cryptographic identity, managed through decentralized authentication servers. Data integrity and confidentiality will be ensured through end-to-end encryption, quantum key distribution experiments, and continuous behavior monitoring. The system will automatically detect anomalies, such as spoofed devices, signal injection, or man-in-the-middle attacks. Indian cybersecurity firms are collaborating with telecom operators to design adaptive firewalls and distributed intrusion prevention systems that work in real time across millions of nodes. Energy efficiency is another core focus of India's sixth-generation research. With the expected rise in connected devices and higher data rates, the network must use power wisely to avoid overwhelming the energy grid. Engineers are experimenting with energy harvesting technologies that allow small sensors and edge devices to operate without batteries by collecting ambient radio waves, light, or vibration. Meanwhile, base stations will use intelligent sleep modes and coordinated wake cycles to minimize unnecessary power usage. The goal is to create a zero-waste communication system where every watt of energy contributes to active data transmission or computation. Interoperability with other systems is being built into India's sixth-generation roadmap from the beginning. This includes integration with satellite communication, Internet of Things infrastructure, unmanned aerial vehicles, and public safety networks. The idea is to create a unified communication platform that can serve agriculture, education, healthcare, defense, and commerce with equal efficiency. Indian regulatory agencies are also preparing spectrum allocation plans that support flexible licensing and shared usage. As trials progress, sixth-generation platforms developed in India may be tailored for different use cases such as mobile broadband in cities or emergency response in disaster zones. In the future, India's sixth-generation networks could support fully immersive digital environments that blend real-world and virtual interactions through advanced holography, real-time language translation, and ultra-low latency tactile feedback. These capabilities may enable remote physical collaboration, such as surgeons operating robotic instruments from thousands of kilometers away, or engineers managing infrastructure in hazardous locations without leaving their offices. Mobile devices might evolve into lightweight wearable glasses, or even neural interfaces that communicate directly with the brain. With continued progress in artificial intelligence, quantum communication, and terahertz hardware, India could pioneer new global standards in human-digital interaction. If successful, India's sixth-generation efforts could result in homegrown telecom platforms that support an entire ecosystem of services from industrial automation to virtual education. Future versions of sixth-generation networks may use satellite links, adaptive antenna arrays, and artificial intelligence-driven resource management to deliver personalized and efficient data flows. These advances could empower India's rural sectors, improve remote diagnostics in healthcare, and support next-generation military and space systems. With continued investment and collaboration, India may not only adopt sixth generation quickly, but also export its expertise to developing nations. This early momentum shows that India does not plan to follow others in technology leadership, but is working to become a core developer in the global digital landscape. Thank you very much for watching. Please like and subscribe.